Okay, let's move forward. In the last class, we discussed the Slater rules and also the use of the Slater rules for the explanation of the electron configurations of atoms. And we discussed one example, that was the example of the potassium, and we saw that we can predict the ground state electron configuration of the potassium very effectively, so we would understand why the potassium is actually main group element, having a 4s valence electron, and not the transition metal element having a 3d valence electron. So here's just one more example that will expand on that. This is a little bit more complicated example. It considers not only one electron, but overall 8 electrons. So we could also look at the iron and ask, well, why is the electron configuration of the iron 4s2, 3d6, and not 3d8, 4s0? So let us apply the Slater rules to calculate the electron energies for the respective orbitals, which we have to consider 8 now. So what is the Slater form of the electron configuration? We see it's a little bit different from the energy electron configuration. So it's 1s2, 2s2, 2p6, 3s2, 3p6, 3d6, and 4s2. And we have to put the right groups of orbitals in parentheses. So the 2s and the 2p will be grouped together, as well as the 3s and the 3p. All the other orbitals are their own group. Okay, so next we have to determine the shielding constant. Okay, so in this case here, we look at the 3D electrons first. Okay, so when you look at the 3D electrons, then we do not need to consider the 4s electrons because they are further to the right of the 3D electrons. So there are 5 3D electrons in addition to the d electron that we look at. So these 5 contribute 0.35 to the shielding constant. Okay, now to that we have to add 18 electrons that contribute 1 to the shielding constant. Okay, why is that? Because we look at the d electron, so all electrons that are to the left of the electron that we look at, they count 100%, and overall these are 18. 2, 4, and 6 are 10, 12, and 6 are 18. So overall we have 5.0.35 plus 18 times 1, which is equal to 19.75. So now we also have to look at the 4s electrons. So we look at one of the 4s electrons. Yeah, but before we do that, we can directly also calculate the effective nuclear charge for the d electrons. So this is then 26 minus 19.75. So 26 is nothing else but the real nuclear charge, because the iron atom has 26 protons, and 26 minus 19.75 is 6.25. Okay, but now really, let's go to the 4s electrons. So the shielding constant is in this case 1 times 0.35. That's because we have one other 4s electron in addition to the 4s electron we look at. Then we have 14 electrons that contribute 0.85. Okay, and these are the 14 electrons that are in the n-1 shell. That's these 6 3p and these 2 these two 3s, so that is actually 8 and not 14. So there is actually, therefore, a mistake. So this should be 8 and not 14. And we have, well, these here, 6, 8, and 10, which contribute 1 to the shielding constant. That is because they are in an n-2 shell. But these ones here, they're actually just, 8 and not 14. So that should be corrected here. Okay. Then the effective nuclear charge would be 26 minus 22.25, which is equal to 3.75. Oh, no, sorry, mistake. I'm looking at the wrong electron configuration. We have to look at the Slater form of the electron configuration, and then we have to consider the 3D electrons as well, of course. So the 3D electrons are left to the 4s electrons. Okay, so we have to consider these in addition to these 8. Okay, and then 8 plus 6, that gives 14. So I'm sorry about my confusion. I looked at the wrong electron configuration. Of course, we need to look at this one here and not at that one. Okay, so everything is good. We can now calculate the energy of the 3D electrons. So that's now the effective nuclear charge square over the quantum number n squared times 13.6 electron volts. So now for the 3D electrons, we calculated that the effective nuclear charge is 6.25. So we have minus 6.25 square over the quantum number n, which is 3 square, because we're looking at a 3D electron here. So times 13.6 electron volts, and that's minus 59.03 electron volts. Okay. Now, we have not only one 3D electron, we have overall 6 3D electrons. Okay. And therefore, considering the energy of all the 6 3D electrons, we have 6 times minus 59.03 electron volts, which is now minus 354.17 electron volts. So now let us look at the 4s orbitals, so the 4s electrons. So the effective nuclear charge was 3.75. So the energy of one 4s electron is minus 3.75 square over 4 square. It's 4 because we have a 4s electron. So this is times 13.6 electron volts, and that's minus 11.95 electron volts. So now we have 2 4s electrons. So therefore we have overall 2 times minus 11.95 electron volts, which is equal to minus 23.90 electron volts. So now for the overall electron configuration, considering both the 4s as well as the 6 3D orbitals, we have then, well, the sum of that here, and that's minus 354.17 electron volts, minus 23.9 electron volts, and that's minus 378.1 electron volts. So now let's compare this to the other electron configuration here. So first of all, we have to write it in Slater form. Okay. So in this case, we do not need to change the order of the orbitals. We only need to put them in parentheses. So again, the 2s and the 2p orbitals go into parentheses, and the 3s and the 3p orbitals go in parentheses. The other ones, they remain their own group. Okay, same process. We start to look at the 3D electrons first. Okay, so we see that we have 7 of them in the same group compared to the one 3D orbital that we look at. So we have 7 times 0.35. Okay, and then we have 18 electrons, these ones here, left to that 3D electron, and those fully shielded. They have a factor of 1, and then 7 times 0.35 plus 18 times 1, that gives 20.45. Okay, now what's the effective nuclear charge? Well, that's 26 minus that value, and that's 5.55. So now in this case, we do not have any 4s electrons to consider because the number is 0. So we can calculate the energy of the 3D electrons directly, and we can directly considering here that we have 8 of them. Okay, so for a single 3D electron, the energy would be minus the effective nuclear charge square, which is 5.55 square, over the quantum number n square, which is 3 square. Okay. Now times 8, because we have 8 electrons, and that's minus 372.3 electron volts. You'll see again that the Slater rules can correctly predict the ground state electron configuration of the atom, because this value here, 378.1, or more precisely, minus 378.1, is somewhat smaller than this value here, minus 372.3 electron volts. Okay, now we should keep in mind that these Slater rules only account for electrostatic interactions between the particles. Okay, so Coulomb forces. Okay, what the Slater rules do not consider is the interaction of the magnetic fields that are associated with the electrons. Okay, so the electrons have a spin, and therefore there is a magnetic field associated with that spin, and of course the magnetic fields of the different electrons having that spin interact with each other. Okay, and they can either interact in an attractive way or in a repulsive way, and that also influences electron energies and orbital configurations, electron configurations. And this is something that the Slater rules do not consider. So generally, and that is stated by Hund's rule, the magnetic fields of the electrons interact usually in the most favorable way according to Hund's rule of maximum multiplicity. Okay, so that means the more unpaired electrons that we have in electron configuration, the more stable that electron configuration is, and the lower the energy of that electron configuration is. Okay, so a consequence of that is that the electron of a subshell is being filled so that the number of electrons with same spin gets maximized. Okay, so now when you look at the two electron configuration that we just compared, then you see that in this electron configuration here that we identified as the ground state electron configuration, we have 1, 2, 3, 4 unpaired electrons, while here we have only 2 unpaired electrons. Therefore, not only from the standpoint of electrostatic interaction, this electron configuration here, 3d6-4s2, is energetically favorable, but also from the standpoint of the magnetic interactions, from the standpoint of Hund's rule, this electron configuration is favored. Okay, this is another contributing factor. Okay, so now we have basically considered all the relevant aspects that determine, well, electron configurations of atom and the Aufbau principle. So let us go through the atoms step by step in order to understand their ground state electron configurations. So we start out with the hydrogen. Well, the hydrogen has only one electron, and of course that one electron goes into the 1s orbital. Then for the helium atom, the second electron, well, needs to go into the 1s orbital also, but it needs to be spin down because of the Pauli principle. So for the lithium, we have 3 electrons. So the 1s orbital is full now, and because of the Pauli principle, we need to fill the third electron into the 2s orbital. Okay, we understand now why the 2s orbital is energetically lower than the 2p orbital. That is because the 2s orbital penetrates the 1s orbital better than the 2p orbital. Remember, we discussed this in the last class. Okay, then for beryllium, we have 1 more electron. Well, that electron would pair the third electron in the 2s orbital. So we will have a full 2s subshell. So as we go from to the boron, we need to start a new subshell because of the Pauli principle. And the 5th electron would go into one of the 2p orbitals. Now from the carbon on, we have to consider Hund's rule. Okay, that means that we have to fill the 6th electron into a different 2p orbital, and we have to fill it with the same spin into the 2p orbital so that the number of spins get maximized. So then for the nitrogen, we have another electron, and that last electron would need to go into the 3rd 2p orbital, also with the same spin according to Hund's rule. So now from the oxygen on, we start to, we have to start pairing spins. So the additional electron would now pair one of the unpaired orbitals in the 2p orbital. And then when we go to fluorine, 2p orbitals are being completely filled with paired electrons. And then at the neon, we have all our p orbitals being filled, and we have a so-called full shell, and we have reached a so-called noble gas electron configuration, which is particularly stable. So now, as we go from neon to the sodium, we start a new shell. So the next electron would need to go into the 3s orbital. So as we go from sodium to magnesium, that orbital would become, that electron would become paired. As we go from magnesium to aluminum, we would have to start this 3p subshell. Then beginning the silicon, we have to consider Hund's rule again and fill additional electrons in different orbitals, maximizing the spin multiplicity. So for silicon, we have 2 spin up electrons in 2 different orbitals. For the phosphorus, we have 3. After that, we have to start pairing the spins. So with the sulfur, we have 1 electron pair. For the chlorine, we have 2. And for the argon, we have again a noble gas electron configuration with a full shell in which all electrons within a shell are being full and being paired. Okay, so now as we go beyond the argon, we will have to go to the potassium, and like we previously discussed, the 4s orbital has a lower energy than the 3d orbital. So the 4s subshell gets filled before the 3d subshell. Okay? Then as we go from potassium to calcium, we will fill the 4s subshell. And after that, starting from the scandium, we will start filling the 3d subshell. So we begin the transition element series with the scandium. So as we go from scandium to titanium to vanadium to chromium, the number of unpaired electrons in the 3d subshell increases. So the chromium deserves additional attention, because one would actually expect an electron configuration 4s2, 3d4, but experimentally observed is an electron configuration 4s1, 3d5. Okay? And that is now due to magnetic effects. Okay? So a half-filled 3d subshell with all electrons spin up is energetically particularly favorable because of the favorable magnetic effects, which in this case offset the electrostatic effect. Therefore, we have an exception here. So from the manganese on, everything is normal again. We fill the 4s subshell completely, leaving the 3d subshell half filled. Okay? And then from the iron on, we have to start pairing the electrons in the 3d subshell. For the iron, we have 1 electron pair. For the cobalt, we have 2. For the nickel, we have 3. Now for the copper, we get another exception. So we would actually expect the electron configuration 4s2, 3d9, but what we observe is the electron configuration 4s1, 3d10, and that is because full 3d subshell is again a particular electron configuration due to favorable magnetic interactions between the electrons. So finally, for the zinc, we have both the 3d subshell completely filled as well as the 4s subshell. So now as we go from zinc to the gallium, we are leaving the transition metals, going back to the main group elements. So for gallium, we have 1 electron in the 4p subshell. For germanium 2, again, we have to obey Hund's rule as we fill in the electrons into the 4p subshell. For the arsenic, we have 3. And then from the selenium on, we have to start pairing the electrons. So for selenium, we have 1 electron pair. For bromine, we have 2. And for krypton, we have 3. And krypton, again, represents a noble gas with the 4th shell being completely filled. So of course, we could continue these considerations, but I'm stopping here at that point because there's nothing too much new to learn. And instead of that, I want to give you a brief discussion of the entire periodic table now. So you see here the periodic table of the elements, and the periodic table of the elements can be explained by the Aufbau principle and the quantum mechanical model of the electron. I should say here that the periodic table of the elements was invented a long time before the quantum mechanical model of the electron was developed. This was originally invented by Mendeleev and Meyer, who ordered the elements according to their masses, and whenever they encountered an element that had a similar property than an element they already considered before, then they started a new row, and that overall gave 7 rows. We call them periods today, and overall 18 groups. Of course, at that time, a lot of elements were missing, but over the time, the periodic table was complete. Today, as we know about elementary particles, we do not order the elements by mass anymore, but by the number of protons. But only in very few cases that changes the order of the elements. So overall, the periodic table wasn't changed very much by making that change to it. So now the quantum mechanical model of the electron now nicely explains the periodic table. In particular, it explains why elements that are within the same group, in the same column, actually have similar properties. Okay. So for instance, the elements hydrogen, lithium, sodium, potassium, rubidium, cesium have a number of properties in common. But why? So when you analyze the electron configurations of these elements, you see that they all have the same number of so-called valence electrons. So these are the outermost electrons that determine the chemical and physical properties of the elements. So why do these valence electrons determine the chemical and physical properties? Because these are the electrons that have the highest energy. So all group 1 elements, which are called the alkaline metals, except the hydrogen, they have all 1s valence electron. Okay. So now in group 2, all the elements have 2s valence electrons. Therefore, group 1 and group 2 are called the s block. Okay. So then next to the s block, there's the d block. So these are all the elements that have d valence electrons. Okay. The number of these valence electrons increases from the left to the right. In the periodic table. So the scandium has 1, the titanium has 2, the vanadium has 3, and so forth. You also see here in this periodic table the exceptions. So chromium, as we discussed, is already 1 exception. Copper is another one. There are actually a few more. For instance, niobium, molybdenum, silver, gold, platinum. We do not have to discuss them all in detail. We shall only make the general consideration here that the electron-electron interactions in atoms can be complex, and that sometimes leads to subtle changes within the electron configuration. So now to the right of this D block, we have then the P block. In all elements in the P block, they have p valence electrons. Okay, so the group 3 elements have 1. The group 13 elements have 1. The group 14 elements have 2. The group 15 elements have 3. The group 16 elements have 4. The group 17 elements have 5. And the group 18 elements have 6. So these, this P block together with the S block are also called the main group elements, and the D block is also called the transition metal elements. Okay. So then, in addition to that, we have the so-called F block. So these are called the lanthanides or the actinides, respectively. So the first row here, that is the lanthanides, standing for elements following the element lanthanum. And this row here is called the actinides, so the elements following the element actinium. Okay. Now, these elements here are actually in this position here of the periodic table. So lanthanum and actinium are actually group 3 elements, and the lanthanum standing below the yttrium and the actinium standing below the lanthanum. So all the remaining ones, these ones here, are actually in between the lanthanum and the actinium and the hafnium and the rutherfordium, respectively. Okay. However, usually that F block is not directly inserted into the periodic table, but placed underneath the rest of the periodic table just for space arguments. Otherwise, the periodic table would just become too wide, and it would be difficult to handle our periodic table. Okay. So now within the F block, the number of F electron generally increases from cerium to praseodymium to the neodymium to the promessium to the samarium to the europium, gadolinium, terbium, dysprosium, holmium, erbium, thulium, ytterbium, and lutetium. Okay. And the same is then also true for the actinides. So the number of F electrons increases from the thorium to the lawrencium. So meanwhile, the entire 7th period is full. Okay, so that means also the P block of the 7th period is meanwhile complete. So these last elements have actually just been added last year. So only by last year, the 7th period of the periodic table has actually been completed. This is an inorganic chemistry class. So therefore, you have to know all the element symbols and the element names and how the elements are arranged in the periodic table. So this requires a little bit of a memorization effort. So everything goes easier with music. So it's actually a nice song by Tom Lehrer. It's called The Elements, that can actually help you to memorize the periodic table. And so in the following, we shall listen to the song, which is here embedded as a YouTube link. So I just click on that here. Yeah, I was just notified that you cannot hear the song. Is that correct? Is that correct? You cannot hear the song?
Yes, sir.
Yes, so that was, of course, unintended because I can hear the song. So I don't know why you cannot hear the song, but I can hear it. I'm trying just to find the song on YouTube directly, not as part of the link here. So let me just get out of this. So now let me just do this. And now let me just share the screen again. Okay, so now I'm playing this again, and hopefully you can hear it. You can see now the screen with the YouTube's webpage. Yes. Okay, now let's hope that it works now.
Professor, we still can't hear it. I think you have to share your sound through Zoom, like share your computer sound in addition to the video.
Yeah, I don't know why this doesn't work. Apparently you still cannot hear that, right?
No, we can't. I think you have to share your computer sound through Zoom, like separately.
So I don't know why Zoom fails on playing this song. Now I don't know why this keeps on playing now. That of course I do not want. I don't want to play this all the time here. So I don't know what to do with this. I don't know how to stop this anymore. So now I've stopped it.
If you go into your Zoom settings, you should be able to ensure that the speaker output is the same as the system so that your audio from your device is also broadcasting through Zoom.
Yeah, but it must do that because I can hear the song. Why am I the only one that can hear the song? That's the problem. If I also couldn't hear the song, we would be all the same, but why can I hear it, but you cannot hear it? That's the problem.
So what is your output speaker setting for your Zooms currently?
I have to check that. Well, I mean, I hear myself. I hear actually through my headphones here. Let me just, how do I maximize this again here? Wait a moment. It's really annoying. It's a bar here. So we have here yeah, I think we are just losing too much time. So I'm sorry that I cannot play you that song, but you have the link to it on the PowerPoint slides. And so you may want to listen to it privately. At least then it should actually work. Oh, you have to share Zoom audio. Okay. Now, how do I do that?
It's an option when you go to share your screen. You can share your screen and your computer sound.
Ah. Okay, share computer sound. Ah, okay. Optimize screen sharing for video clip. Let's do that as well. So that should make a significant difference. Okay, so let's try this again. So let me close this. So which screen do I share now? Let me go back to the PowerPoint slide. So this is presentation 6. So we share this again. Okay. So I start this. So now I start the song again here in the PowerPoint slide. So now hopefully you can hear it. Can you hear it?
Yes.
Good, excellent.
There's antimony, arsenic, aluminum, selenium, and hydrogen and oxygen and nitrogen and rhenium, and nickel, neodymium, neptunium, germanium, and iron, americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, and lanthanum, and osmium, and astatine, and radium, and golden protactinium, and indium, and gallium, and iodine, and thorium, and thulium, and thallium. There's yttrium, ytterbium, actinium, rubidium, and boron, gadolinium, niobium, iridium, and strontium, and silicon, and silver, and samarium, and bismuth, bromine, lithium, beryllium, and barium. There's holmium and helium and hafnium and erbium and phosphorus and francium and fluorine and terbium and manganese and mercury, molybdenum, magnesium, dysprosium and scandium and cerium and cesium and lead, praseodymium and platinum, plutonium, palladium, promethium, potassium, polonium and tantalum, technetium, titanium, tellurium and cadmium and calcium and chromium and curium. There's sulfur, californium, and fermium, berkelium, and also mendelevium, einsteinium, nobelium, and argon, krypton, neon, radon, xenon, zinc, and rhodium, and chlorine, carbon, cobalt, copper, tungsten, tin, and sodium. These are the only ones of which the news has come to Harvard. And there may be many others, but they haven't been discovered.
All right, very good. Finally, we got it. So listen to the song, memorize that song, and you know your periodic table. Okay, so now let's move on. And let us look in more detail. Let's look in more detail. What the periodic properties of the elements are. So basically, periodic properties of elements are properties due to the position of these elements in the periodic table. Okay. So now the first periodic property that we want to look at is the atomic radius. So you see here the periodic table, and you see the atomic radii of the atoms. Okay. So generally recognize that the atomic radii vary from tens of picometers to hundreds of picometers in general. So the one with the smallest atomic radius is actually the helium that has a radius of 31 picometers, and the largest one here is the cesium, which has 298 picometers. But now, what are the trends across a period? So we can see that when we go from the left to the right within a period, the atomic radii tend to decline. So this is our first periodic trend that we want to consider. So within a period, the atomic radius tends to decrease. You see, that's also true for all the periods, from helium, from hydrogen to helium, from lithium to the neon, from the sodium to the argon, with pretty much no exception. So now, what is the explanation for this? So as we go from the left to the right in the periodic table, we are actually adding protons and we are adding electrons. So despite we are adding electrons, the atomic radius tends to decline. So why is that? That is because when we add electrons within the same period, we are adding electrons to the same shell. Okay. So these electrons have additional electrons have a similar distance to the valence electrons that atom already has. Okay. So now there will be some more electron-electron repulsion between the electrons because we have one more electron to consider. But on the other hand, because we also add a proton to the nucleus, there's also, well, additional Coulomb force that the electrons experience. So there are basically two factors that oppose each other. And now, if we add electrons to the same shell, basically the effect from the Coulomb attractions between the electron and the nucleus is somewhat greater than the electron-electron repulsion. And that leads to an overall decrease of atomic radius. So now, however, we see an additional trend, which is that as we begin a new period, our atomic radius suddenly jumps by a lot. Okay, so how we explain that? Well, when we start a new period, then we start a new shell, and that electron will now be much further away from the nucleus in comparison to all the other electrons. And that additional electron will be very well shielded. So the effect, the nuclear charge acting on that additional electron will be very well shielded by the electrons which are actually below that electron. And for these reasons, our atomic radius jumps as we begin a new period, and that's true for all periods. Okay. So now the third trend is that within a group, the atomic radius tends to increase. Now one can explain that trend just by the combination of the first two trends. So within a period, the atomic radius tends to decline, but not all that much overall. But as we start a new period, the atomic radius well jumps dramatically, which is a large effect. So overall, within a group, the atomic radius tends to increase. Can also explain it a little bit differently and say, well, within a group, we change the, well, quantum number n as we go down a group. Okay. So therefore, we are always adding shell as we go down the group, but having the same kind of valence electron configuration. So therefore, of course, we would expect that our atomic radius increases as we go down the group. So these are the overall three trends to consider. So I see we are out of time, so maybe let's stop at this point, and I just stop the recording here.